Alright, after 5 minutes break, let's continue the topic in section 4, the net change theory. We are going to look at the definite integral, the integrand function fx in a different way with some interpretations, okay, with some interpretations. So here, according to FTC, okay, according to FTC part 2, we know this formula. Okay, we know this formula. And you will see that we repeat those FTC again and again, which means this theory is important and we need to apply those in go through with the definite integral. Now, here, I should mark, oh, I have the notation, okay, I have the notation. The big F in the first one, okay, in the first one, the big F, we understand the big F is any antiderivative, which implies the derivative of big F, right? Which implies the derivative of big F gives the small f. So somehow we can replace the integrand fx. Since f prime x gives the small f, right? Since f prime gives the small f, so we can replace the integrand, the f, small f inside with the f prime, right? With the big F prime. And here we should recall the interpretation of derivative, okay? Interpretation of the derivative we did in the interpret the derivative in chapter 2. Now we rewrite the integrand small f as big F prime. Now, what is the big F prime? How can we interpret this one as the rate of change? We know we can interpret the derivative as the instantaneous velocity and the rate of change, like that, right? So f prime we can interpret as the rate of change, in f, and we usually write the function y equals fx, big F, okay? If we have y equals big F, then how can we interpret f prime? The rate of change in y with respect to x, right? With respect to x. We need to recall the interpretation of derivatives in chapter 2. So if we know the big F, we let the big F is y, okay? The big F is y. The derivative of big F, we can interpret it in this way. The rate of change in y or in fx with respect to x, right? So that is the rate of change of big F with respect to x, right? With respect to x. Sorry. So here the f prime represents the rate of change of y, fx, with respect to x. How we interpret if we replace this small f, okay? And what does fb minus fa mean now? What does this difference between the function big F at the two endpoints? So that is the change in y, right? That is the change in y when my x changes from a to b. So here, this one actually implies the function change, right? The function value change from a to b. Make sense? So that is the way we rewrite the FTC part 2 and replace the integrand small f as f prime as the derivative, and we recall the interpretation of derivative. So this is rate of change, right? Then that will be the function, okay? That will be the function change from a to b. That equals the function change from a to b. And we know this is the function big F. This is its rate of change, its derivative, right? If we give function big F some interpretation, some background, then it will be easy to understand. Okay, it will be easy to understand. So let's check the net change theory. The integral of a rate of change is the net change. Okay, this one is called the net change, which this part is called the net change in y, right? Net change in y, fx from a to b, right? From a to b, or when x changes from a to b, and we know what does this part mean. This is the same as a to b, small fx dx. This is the net area, right? The left part is the net area. So that is the net change, right? Now, let's see some applications if we give the interpretation for the big fx, okay? For the big fx. Now, I'm going to mention a quick one, okay, in economics. For example, my fx is the cx, which is the cost function, okay? Cost function. I'm just give you, this is in one field, economics, okay? Number one in economics. So if my big F is the cost function, cx, okay, cx, then c prime, the derivative of f, that is called the marginal cost function. Marginal cost function. Then how can we evaluate it from a to b, the marginal cost function? How can we evaluate this one? How can we evaluate it? This is marginal cost. This is the rate of change, actually, right? The rate of change of cost of function, we give the name, that is marginal cost function. So according to FTC, that will be the function fx, that will be the change, the net change in function big F, which is cb minus ca. That is the net change. This part is the net change in cost function, right? The net change in cost function cx from a to b, right? From a to b. So we can apply the definite integral in this kind of case, okay? In this kind of case. So that is number one in economics. And I know you guys are engineering people, right? You don't care too much about the economics. And we will focus on the physics, okay? We will focus on one application in physics. And we already did some application for the differentiation in the physics part. And we already understand the relation between acceleration, velocity, and position, right? So if an object moves along a straight line with position function st, then its velocity is vt. What is vt? Derivative of position function st, right? S prime t. Or we can understand this one as velocity is the rate of change of position function. So the change in position from time t1 to time t2, we need to finish the change in position, okay? The change in position function, which means the change in st. Now this st is my big ft, okay? Is my big ft. So that will be t1 to t2, t1 to t2, s prime t. What is s prime t? Which gives velocity function, right? Velocity function. Here, independent variable is t, so should write dt. Then that equals the change in position st2 minus st1, right? So we can work out the change in position from T1 to T2 with this definite integral. Okay, with this definite integral. Again, this is still it's still the area. It still represents the net area. But now we should understand, what does this area mean? This area is the change in position. Okay, this is the change of the position for one object. Okay, now let's look at the acceleration. So the acceleration of the object is at equals v prime t. Acceleration is the rate of change of velocity function. So is the change in velocity. Now what is my fx here? The first one, my big F, I'm talking about. The big F is my position function. In the second case, what is my function? You can use t. Okay, you can use t. Sorry. Let's use the independent letter t. So here my function is ft. So in the first case, my big ft is position function, and then f prime t, that is velocity. Now for the second one, my ft becomes the velocity. Then take the derivative, the rate of change of f, that is acceleration. So the change in velocity from t1 to t2, right? That will be v t2 minus v t1. How can we evaluate it? How can we evaluate those? That will be the definite integral. Okay, the definite integral with the integrand f prime t. Now my f is this one, f prime t, which is acceleration. Okay, which is acceleration. My voice is a little bit low. How about the other people? I guess should be fine. We don't have any voice problem in the morning. Okay, so these two give us how can we evaluate the change in ft, okay, in position change or in velocity change. Use the definite integral. Okay, use the definite integral. Now let's check the examples. Okay, let's check the example come from physics with two-part questions. Example 1. A particle moves along a line so that its velocity at time t is a quadratic function vt. It's about t. So someone said they cannot hear me. How about other people? I just need to make sure, is it just one person's internet problem? How about the other people? Can you hear me? Can you hear me? Okay. So most people are good, right? So just maybe one or two person, you have your local internet problem. Yeah, let me continue on this example. Okay, so the velocity function is a quadratic one, and we know the velocity is measured meters per second, right? The standard international unit for velocity, meters per second. That is a quadratic function. Then find the displacement of the particle during the time period between 1 and 4 seconds. Part B, find the distance traveled during this time period. Question A asks displacement. Question 2 asks the distance. Displacement is the same as the position change. Okay, is the same as the position change from 1 second to 4 seconds. And distance means how. By the way, the position, the displacement, that is a vector, kind of vector. They have the direction. We can have positive and negative directions, but distance is the non-negative values, right? Distance is the non-negative value. We cannot have negative distance. And by the way, let me mention to you, how can we interpret those in Chinese? Okay, just recall some of your Chinese knowledge. Position is called 位移, distance is called 距离. they are different. Also in Chinese, they're different concept. Okay, that's what I said. When we talk about displacement or the position, it means we have the positive, we define the positive and the negative. We have the direction. Usually we will define from left to the right is positive. We will usually define this one. So if we have the object moves from the right side to the left, that will be negative, right? That will be negative. But the distance should be a non-negative numbers, okay? Non-negative numbers. So here, let's answer part 1, okay? Let's answer part 1. Yes, interesting to recall some Chinese knowledge. 位移, 距离. Part A. Find the displacement, which means find the position change from 1 second to 4 seconds. So it should be S4 minus S1, right? Because the time period shows from 1 second to 4 seconds. So according to the net change theory, that will be 1 to 4, the derivative of position, which is Vt, right? Which is S prime t dt. Don't forget your term dt. Now, what is my Vt? My Vt is a quadratic function t squared minus t minus 6 minus t kind of physics class. Yeah, somehow we recall some physics knowledge here. So dt, okay, dt, and then we are going to evaluate the definite integral, right? We are going to evaluate the definite integral, which means you should find the particular antiderivative t squared t cubed over t. I'm not going to call anyone to answer the question, okay? Usually no one answered. Some volunteer answered. The people I selected, they are not available. T squared over 2. T squared antiderivative should be t cubed over 3. T should be t squared over 2 minus 6t, and then evaluate it from 1 to 4. And here you can finish the calculation later, okay? The answer should be minus 9 over 2, okay? Minus 9 over 2. How can we interpret this displacement? How can we interpret this displacement? Minus 21 is not right. So the answer we get minus 4.5 meters. That means from T1 equals 1 second to T2 equals 4 seconds. The particle moves which direction? If follow the direction we define, we get the minus number for the position change. That means the particle moves toward left, okay? Moves toward left, which means this one from right to left moves toward the left, minus 4.5 meters. 4.5 meters. This is how we understand the position change gives a negative number, okay? The position change gives a negative number. So moves toward left 4.5 meters, okay? Moves toward the left 4.5 meters. Now, that is the first question, okay? That is the first question how we answered. Now let's check the solution here. So by the equation about the change in the position, the displacement can be worked out in this way, okay? Evaluated at 1 and 4, and then you calculate the values, okay? You calculate the value. So this means the particle move 4.5 meters toward the left. That is part 1, okay? That is part 1. Let's check part 2. find the distance traveled during this time period. And again, this time period should be 1 to 4 seconds. T is between 1 and 4 seconds. The distance traveled. So here we need to check out. Okay, we need to check out whether from 1 second to 4 seconds, whether the particle always moves from right to left, or it get backward. The particle moves backward and then move to the left again. So it might be this particle moves this side and then moves backward. This is called backward. This is minus. This is positive. And then it moves to the left again from 1 second to 4 seconds, right? And I guess we analyzed one example in chapter 2. We did like that. So the distance traveled, we should count all those 3 parts, right? So here we need to analyze the velocity, okay? We need to analyze the velocity to check the direction the particle moves based on the velocity. Now my velocity is the quadratic equation, and it will be easy to factorize in this way. Okay, it will be easy to factorize t minus 3 times t plus 2. Okay, so now let's check in which case we solve the t. Okay, let's solve the t if we have the velocity is non-negative and the velocity is negative. Let's solve for the t. Okay, let's solve for the t. If the velocity is non-negative, that means each term should be both positive. Both terms should be positive, or both terms should be negative. Then the product we can get is non-negative. And we know when velocity is 0, that means t is 3 seconds or minus 2 seconds. Okay, minus 2 seconds. But be careful. The time is non-negative, right? The time cannot reach negative numbers. So in this case, how can we solve the t when velocity is non-negative? Both terms should be positive, so t should be greater than 3, right? When t is greater than 3, equal it's 0. I'm talking about greater than 3. This is positive, so we get velocity is positive. Or t is less than minus 2. T is less than minus 2, negative. T is less than minus 2, negative. So both negative also gives the velocity is positive. But t is negative. This part should be removed because it's about time, right? It's about time. Time should always be non-negative. So the velocity is positive. The velocity is non-negative then when t is greater than or equal to 3 seconds. Now let's solve when velocity is negative. Velocity is negative, which means one of the term is positive, the other term is negative, right? One positive, the other negative, then the product will give the negative. The product is the velocity will give the negative. So my t should be between minus 2 and 3. But since t is non-negative, so my t should be greater than 0 and less than 3. Try to follow this part. Okay, try to follow this part. So when velocity is negative, that is the time between 0 and 3. Okay, so that is, let's analyze. Okay, let's analyze the motion procedure. Okay, the moving procedure. We need to understand the procedure, then we are able to answer the questions. Okay, moving procedure of the particle. And I think we did this seminar analysis in chapter 2 when we're talking about the differentiation. The moving procedure of the particle from T1 0 second to T2 3 second. The particle, what is the sign for the velocity? Velocity is negative, right? Velocity is negative. Velocity is negative, which means the particle moves from right to moves toward the left, toward to left, to the left, right? Toward to the left, which means moves from the right to the left this way, right? The particle moves in this way from 0 to 3 seconds. And then when t equals 3 seconds, velocity is 0, right? V3 is 0. There is no problem here. When t is 3, that means particle stops. Particle stops. And then after 3 seconds, Vt is, after 3 seconds, Vt should be positive, which means move toward to the right, right? After 3 seconds, sorry. So move toward to the right. Move toward to the right, which means the particle, after 3 seconds, the particle moves from the left to the right in this way, right? That is the whole moving procedure we analyzed here. Then what is the question they ask? We care about 1 to 4 seconds. 1 to 4 seconds. So that means from 1 to 3 seconds, that is moving to the left. And from 3 to 4 seconds, that is moving to the positive, right? Moving to the right direction. Make sense? Now let me use a different color to denote it. Okay, with this part, okay, with the part 1 and part 2. Okay, so here part 1, when t is 1 second to 3 seconds, toward the left, right? Toward the left. And what is the sign? What is the sign for the velocity? Velocity is negative, right? Velocity is negative. So here the position change. This part is moving from right side to the left side. So here the position change you evaluated with the definite integral. That means it's a negative one. But the question, the distance traveled, you should change it into positive, which means you take the absolute value, right? And then the second part is when t is greater than 3 and between 4, that is toward the right. And this case the velocity is positive, right? The velocity is positive. And here we don't need to worry about the sign of the position change. It gives a positive. It gives a positive. So we need to care about the position change from 1 second to 3 seconds. Okay. Now let's check the solution I typed here. So note that the velocity function we can factorize in this way. And then when velocity is they put equal both, okay, when they including the endpoint. So when the velocity is negative for in the interval 1 second to 3 seconds, that means the particle moves from the right to the left. That is the negative, right? That is this direction is negative and this direction is positive, right? So the positive part is when we have the time from 3 to 4 seconds, right? 3 to 4 seconds. Then the distance traveled we separate into two parts, okay? So the position change will be 1 to 4 seconds, right? But we need to evaluate the distance, and we know from 1 second to 3 seconds, that is the sign for the position should be negative. The velocity is negative. So we put, this is the negative. So we put a minus, which means we take the absolute value here, okay? Which means we take the absolute value because the velocity is negative. So we take the absolute value inside the integrand. So that is minus, okay? That is minus. But from 3 seconds to 4 seconds, we don't need to worry, okay? We don't need to worry about this part. And this part you solved should be a positive number. It's the distance, okay? It's the distance we traveled here. So that's why we analyzed the time, okay? Because if you couldn't analyze the time, at which time the particle move, the velocity is negative, at which time interval the velocity is positive, then you are not going to separate the 1 to 4, okay? You can't separate the time from 1 to 4 seconds in that way. Okay, that's why we know it's just apply the net change theory from from T1 to T2, the rate of change of position function velocity Vt dt, that is st2 minus st1. But that is only the question for the displacement or the position change from T1 to T2. With the physics background, sometimes they will ask the distance traveled, okay? So don't blame on me, okay? It's not my responsibility. I'm only responsible of the mathematics part, okay? So it's tricky, okay? It's tricky from your physics subject why they ask this kind of question. The distance traveled, which makes a little tricky. We need to figure out the direction of the velocity. Okay, so sometimes with the background, the problem becomes more complicated. You need to analyze those. So what I did in the previous slide, write a lot of notes. That is your physics and analyze. Okay, that is your physics analyze. Now there is one quiz. Okay, there is one quiz to evaluate the definite integral with the function x cubed minus 6x. I guess it will be easy. Okay, it will be easy. Let me set up 5 minutes. Okay, 5 minutes to try the quiz. And don't share your answer, okay? Don't share your answer. If you know the answer, just submit your own answer in the slides, okay? By the way, how to participate the quiz, the pop-up quiz in the Rain classroom, we practice it before the first week. We practice this part. It's not showing in the category question or quiz. It's just the last page of my slides. Here with this question, we have A, B, C, D, different choice. You just choose one of them, okay? You just choose one of them.